a pleasure for us in the line seminar to welcome today's speaker, Alessio Figalli from ETH Zurich, and he will tell us how to solve the Giorgi conjecture for the free boundary Alencani function.
Okay, thank you, Esther. Thank you. So, yeah, thanks for having me here. So I will try to give a Blackboard style talk. And let's see. So what I want to focus here is the Giorgi conjecture in the free boundary setting. But before getting there, I will spend a bit of time to first, put together the setup, introduce the setup, what is this about, and how this has evolved as a problem. So let's start from some preliminary discussion. So first of all, I want to discuss a moment area minimizing surfaces. So I don't call them minimal surfaces just to avoid, because some people minimal surfaces are just critical points. So these are area minimizing. So what is this about? You are in a REN and you have some gamma, which is n-2 dimensional, like a smooth n-2 dimensional surface without boundary in the ambient space R capital N. And you want to find a surface sigma that minimize the area among all surfaces that bound gamma. So you minimize the area of sigma with the constraint that the boundary of sigma is your gamma, which is given. So this problem can be set up. There is a framework for this. This is called the framework of currents. I will not discuss what they are, but this is just a generalization of classical surfaces, a bit like Sobolev spaces for smooth function. You have a bigger framework to prove existence of these objects. And in the framework of currents, there exists a minimizer. So minimizers exist. The challenge is to understand how smooth they are, because a priori currents are not smooth objects. And the general theorem that you can prove in this setup is the following. So theorem sigma is smooth outside a singular set of dimension less or equal than n minus m. So this minimal surface can have a singular set. This set is lower dimensional. And what is m? M is the smallest.
For example, you file on to come out, you just come out and you follow your nearest one. So to get the quickest route out of the building for me would just be
I think someone is speaking. It's not muted. Okay. Is the smallest dimension where singular minimal cones exist. So what is this? So you change the dimension, you look at smaller dimensions, little m, and then you ask yourself, if I am in dimension m, can I find a singular minimal cone in such a dimension? What is a minimal cone in such a dimension? Is a cone is something like this. So C is a cone. It means that to be a cone, it means that if you take C and you dilate by R plus, you get C itself. So C is invariant of the dilation. If you multiply, this is the origin, 0. And C is locally area minimizing. Okay, so you always have a trivial minimal cone, which is the hyperplane. A hyperplane is a cone and is area minimizing. But the question is, are there dimensions where minimal cones exist and they're not just a hyperplane? And the famous theorem by Simons well, Simon's, let's say, build example, and then Bombieri, De Giorgi, and Giusti prove the theorem, the final theorem. So this is 68, 69. The theorem says that if you take the cone C, which is given by the set of points of the form x equal y, where x is in R4 and y is in R4. So this is a cone in R8. This is minimal. So this is area minimizing. This is area minimizing. So in dimension 8, you can find a singular minimal cone, which means that sigma for minimal surfaces, sigma is smooth up to a singular set of dimension almost n minus 8, because 8 is our critical dimension. Okay, so this is how things work for minimal surfaces. Now, I will introduce a different setup. I will come back to minimal surfaces in a moment, but first I want to make the parallel from minimal surfaces to Allen-Cahn. So what happens is the following, right? So in the 60s, the 70s, there have been a lot of developments about minimal surfaces. And then the kind of idea that was introduced by the Giorgi was, can you approximate minimal surfaces using solutions to PDE? So the idea is the following. So let me discuss a PDE approach to minimal surfaces. So let's say that I have a domain omega. I have to set up now in PDE sense. So I have a domain omega, and I want to minimize. So I have some function. So maybe, and now I have a function u from omega into R. And what I'm going to do is to minimize some energy. And the energy is the following. We're going to minimize an energy in omega, which consists of two parts. A part which is like Dirichlet type energy, gradient square over 2. And the second part, which is a potential energy, W of u. So what is W? W is an energy profile that looks like this. So I have minus 1, 1, and W is something like this. So I'm looking for functions u which are bounded between 1 and minus 1. So outside I don't care. And I'm looking for functions that, what do they want to do? They want to minimize this potential energy here, right? Maybe let me, yeah. They want to minimize this potential energy here, W, which means that they want to be as close as possible to 1 and to minus 1, because that's where the energy is minimal. At the same time, every time my function u changes from 1 to minus 1, because 1 and minus 1 are the two minimal points, to go from 1 to minus 1, sorry, they pay some transition energy. So this is gradient square. It's the part of the energy that makes you pay something every time you want to transition from minus 1 to 1, or vice versa from 1 to minus 1. So if you just minimize this energy, well, the minimizer is trivial because you just take either 1 or minus 1. So to avoid this trivial minimizer, let me add a constraint. Integral of u equals 0. So let's say u has 0 average. So u has 0 average, it means that sometimes has to be equal to 1, sometimes has to be equal to minus 1. Okay, now let me do a second thing. Let me put a parameter that kind of makes, so if you just solve here this energy, you will just get a smooth minimizer that will go from minus 1 to 1, and will solve a nice PDE in omega. But now let me make it singular, this problem. Let me add a parameter 1 over epsilon in front of the potential and a parameter epsilon in front of the gradient. So this means that now the potential energy is very strong, which means that I pay a lot not to be close to 1 and -1. And the gradient term is not strong anymore, which means that transitioning is not so expensive. And now what I expect here is to have a picture like this. I would expect U epsilon, the minimizer, to be, let's say, close to -1 somewhere, U epsilon to be close to 1 somewhere else, and then there will be a region here, a transition region, where you, so this is the transition part, where you kind of go from -1 to 1. And this is where the gradient energy lives. And the theorem that Modica and Mortola proved in 77 is that as epsilon tends to 0, U epsilon will converge to the indicator function of a set A minus the indicator function of the complement. So A is just A just corresponds to this part of the domain, right? The part where U epsilon is equal to 1, and then omega minus A is the complement. And what the theorem says, so okay, this is the easy part, but then the theorem says is that the boundary of A is area minimizing. So you are getting the transition between the two phases, it's an area minimizing surface. So you're finding minimal surfaces. So you can think of this. So in other words, for epsilon small, the set, let's say U epsilon equal lambda looks like boundary of A, minimal surface, for every lambda between -1 and 1. So, okay, the quantifiers, you have to do that properly, but let's say you fix a lambda between -1 and 1, and then as epsilon goes to 0, this will converge to the minimal surface, each level set. So your level sets are approximating minimal surfaces. And now you can try to look at this problem in a REN, and instead of a local domain. So in a REN, you can, so the remark is the following. So now, so in omega, Laplacian of U epsilon solves a PD, which has a singular term, is 1 over epsilon square W prime of U epsilon, because of the epsilons around. But what you can always do is rescale. And then in the domain omega over epsilon, so if you stretch the variable, when you just make the domain very large, you consider U tilde epsilon of x, which is U of epsilon epsilon, U epsilon of epsilon epsilon, and then this new function solves Laplacian of U tilde epsilon is just W prime U tilde epsilon. So in a bigger domain, if you stretch, the PD becomes again Laplacian equal W prime of something. So it's a nice PD, but now the domain is huge. And what we know by the local argument, by Modica-Mortola result, is that for epsilon small, the level sets of U epsilon looks like minimal surfaces. And then you expect the same for this new function. So the level sets are close to a minimal surface. So this is all heuristic, but then based on this heuristic, in 1978, De Giorgi made a conjecture. He said, okay, let U solve the global PD, Laplacian of U equal W prime of U. And now U is defined in the full space Rn with values in, let's say, -1, 1. And let me make an extra assumption. So assume that Dn of U is strictly positive. what does it say? It says that this function has a preferred direction where it increases. So it means that if this is r n minus 1 and this is r, then the level sets of u equal lambda, are in graphs in the last variable because the function u is increasing. And then, so we assume this, and then if n is less or equal than 8, then u equal lambda is a hyperplane for every lambda, which means u is one-dimensional. So the Giorgi conjectured that in dimension at most 8, the level sets of these solutions to this PDE should all be actually hyperplanes. And why did he conjecture that? Because it says, okay, these level sets look like, from far away, they should look like minimal surfaces. And up to dimension 8, I cannot build a minimal surface which is different from a hyperplane. So in a dimension 8, I told you before that in dimension 8 there is the Simon's cone, the cone of before, but that cone is not a graph. So that's why the result should be true also up to dimension 8. So the example of the cone I gave before, is not a counterexample here, because here I'm looking just, these level sets are graphs. So they're graph over Rn minus 1. So you're gaining a dimension. But the kind of parallel that the Giorgi made was really make a connection between minimal surfaces and level sets of solutions. And out of the results of minimal surfaces, he started to make conjectures about level sets of solution to PDE. And the theorem that we know now, so the state of the art, I would say, is the following. So conjecture is true if, so n is equal to 2. This is due to Gusub. Sorry, let me write. Gusub Cui, 98. So it already took 20 years. 2 years later, Ambrosio and Cabret managed to do the 3D case. In the next decade, the case of dimension between n 4 to 8 was solved by Savin. The paper is 2009, but you have to assume that u tends to plus or minus 1 as xn tends to plus and minus infinity. So there is an extra assumption in Savin's result. So he's not only asking for monotone graphs, so like in the Giorgi, but he also has to ask that as you go to plus infinity and minus infinity, you really reach plus 1 and minus 1. And this is, well, it's a great result. It's an amazing result. Just it has this extra assumption compared to the original conjecture. And then for n equal 9, is false. The conjecture is false. Well, the conjecture is true because the Giorgi already said n less or equal than 8. So false in the sense that there exists a counterexample. This is due to Del Pino, Kowalczyk, and Wei. And this was also 2009. So it's built starting from the idea of the fact that there exists the Simon's cone in dimension 8. Out of that, you can build a graphical solution in dimension 9, and then there is a way to build a solution here. To show that the result would be false. So in dimension 9, you can build a global solution of this PDE. So let's go back. You have a solution of this PDE here, which is monotone, and where the level sets are not graphs. Are not hyperplanes, sorry. So just to be precise, most of these theorems are written, so remark. So usually, the model case is W of U is 1 minus U square over 2. This is a very classical potential that you can put. It's a potential which is which satisfies exactly my assumption. So it has minimum in plus and minus 1. And then the PDE becomes Laplacian of u equal u minus u cube, which is called Allen-Cahn. So the usual model is this one. But most of these results never use the Allen-Cahn structure. They work for every W. Okay, so this is about minimizers. So this is more or less the state of the art for this Allen-Cahn conjecture. Now, let's go back 1 second, and let's talk again about minimal surfaces. Okay, so minimal surfaces are, I told you, are for me, okay, sorry, no, I shouldn't say minimal surfaces. Area minimizing surfaces are surfaces that minimize the area. Now, let's drop the area minimizing assumption, and I just want to assume infinitesimal conditions. So let's talk about stable minimal surfaces. So they're not area minimizing. What are they? So these are surfaces, like before, sigma, which have the following property. So first assumption, they have to be minimal, and then you will see the second assumption is that they have to be stable. So what does it mean to be minimal? It means the following. You take X as infinity and compactly supported vector field from Rn to Rn. Rn to Rn. Sorry, I wrote. So C infinity compactly supported from Rn to Rn. And then what you do, so you assume also that X, the support of X intersection the boundary of sigma is empty. So the X doesn't touch the boundary, the support of X doesn't touch the boundary of sigma. And then you look, so you define sigma of t to be the image of your surface under this vector, under the deformation generated by this vector field. So you can either flow the vector field or you can just do identity plus dx. If you're in a Rn, you can just do this. If you were on a manifold, you will have to do some flow, but that's just a detail. Okay, so I do a variation. So I'm just perturbing my sigma. So my sigma was my surface, and I'm using X to move it somewhere. And then my first condition is the minimality. So I assume that the derivative of the area of sigma t for t equals 0, this has to be 0. And this must be true for every X. So every time I deform my surface, the area does at first order doesn't increase. And this is equivalent to asking that the mean curvature of sigma vanishes. So this is what it is, a minimal surface. It's a zero mean curvature surface. So that's first assumption. Now, what about stability? Stability means that if I do the second variation of the area, this is now non-negative for every X. What does it mean? This corresponds to a sort of Poincare type inequality over sigma that tells you that the integral over sigma of grad phi square is always greater or equal than the integral over sigma the integral of sigma of a square phi square for every phi which is infinity. Sorry, I'm always writing too much to write. For every phi C infinity and compactly supported in sigma. So yeah, here the relation is like that phi, you have to think X is like phi times the normal of the surface to the a normal bundle to the surface. Okay, so this is the stability condition. So let me just write this in brackets. So I'm asking now that I have a surface which is zero mean curvature and is stable. And now the question that people have been asking for 50 plus years is the following. I give you a sigma which is immersed, complete, connected, two-sided, or let's say if you prefer orientable, and stable minimal surface. Then is sigma equal to a hyperplane? So that's the question. So the answer is clearly no for n equal 8, because we have the Simon's cone, the one I already discussed before. But you can ask this in lower dimension, because now I'm not looking at minimizers anymore, so I cannot rely on the previous theorem that I stated. I just have stability. So the answer is yes for n equal 3. And this is, there have been essentially 3 different proofs. There is a proof by Pogorelov, the first one, Do Carmo, and Peng. So Pogorelov, Do Carmo, Peng, and then Fisher, Colbry, and with Rick Schoen. And essentially, they're all in the beginning of the 80s, 79, 80, 81. They're all at the same time. So n equal 3 has been solved 45 years ago. And then essentially nothing happened for 40 years until the case n equal 4 has been solved by Chodosh and Lee in 2022. And after that, there has been a work of Chodosh, Lee, Minter, and Stryker for 24, and then n equals 6, Mase, n equals 4. 24 again. 2 months later. And n equals 7 is still open. Sorry, still. Okay, so we still don't know. So yes, up to 6 at the moment. No for 8, 7 is open. So, okay, I will not enter into this, but I just wanted to use this as a motivation to do the parallel now. So the same parallel I did for minimizers. I will go with the other one. So let's try to make the parallel. So I want to discuss now the stable, the Giorgi. So I start from Laplacian u equal W prime of u. And then as before, but now I'm gonna, so this is like solving the PD. I need to put a stability condition, okay? So stability, so this is like the analog. You have to think of this as the analog of mean curvature Ziegler. And actually, maybe let me go back a second. You have to think of this assumption by Savin here. This assumption, the fact that u converges to 1 as xn goes to plus and minus infinity, this is like area minimizing. So it is being a minimizer, being locally a minimizer. So this assumption of Savin is exactly the gap to go from essentially critical points to area minimizing, okay? So that's why this assumption, which looks innocent, is not so innocent. So so solving the PDE corresponds to minimals to have a mean curvature 0. And now I want to put a condition which is just the parallel of stability. What is that? I take the energy, and then I assume that if I do the second derivative at epsilon at t equals 0 of the energy, so grad u plus epsilon plus t phi square over 2 plus w of u plus t phi. So this is just the energy when epsilon is 1. I assume this is non-negative. And this corresponds to say that grad pi square plus w second u phi square is non-negative. For every phi, let's say, is infinity and compactly supported. So you see, this corresponds a bit to the Poincare inequality on the minimal surfaces. There you have the second fundamental form. Well, actually, I forgot to say. A is the second fundamental form. Fundamental form. And this Poincare inequality on surface is exactly the analog of this stability for Allen-Cahn. And now the question becomes, U stable n less or equal than 7, does it imply U is 1D? And okay, let me try to make a comment now about the two results, the classical de Giorgi and the stable de Giorgi. So here you see in this formulation, here I'm not assuming the monotonicity anymore. So de Giorgi, there was assumption dn of u positive. This is gone now, okay? I'm just assuming stability. And a priori, this looks kind of disconnected, these two results, but actually they're not. And the reason why they're not, so the reason why they're not is the following. So there are two facts. So fact one, d and u positive implies u stable. So actually, so assuming monotonicity is stronger than assuming stability. And then fact two, if d and u is positive, then also you can consider the following functions: u plus and minus of x prime. These are the limit as xn tends to infinity to plus or minus infinity of u of x prime xn. So you take the function and you take the limit of plus infinity and minus infinity, which exists by monotonicity. And now these functions, so u plus and minus, go from Rm minus 1 to R, and u plus and minus are stable. And then if you actually play with this, there is a theorem that says that this is due to Savin, that stable the Giorgi conjecture, so the conjecture of the Giorgi for stable solution in Rn minus 1 implies the classical de Giorgi in Rn. So these conjectures are a bit all connected. And in particular, the stable de Giorgi is stronger, as it is for minimal surfaces. And it also even allows you to gain one dimension. And okay, this is the conjecture. And so far, the only theorem we have is the one by Gussub and Guin in 98 that proves that stable conjecture is true for n equal 2. So yeah, so that's the picture. So in fact, for the stable conjecture, essentially almost nothing is known because we only have it in the plane so far. And it is a beautiful conjecture, just is very challenging because you don't have minimality anymore. Okay, so maybe before okay, let me stop a second and let me ask if there are some questions about what I've been discussing so far about the parallel. And then maybe I will go on and try to set up the free boundary version of this problem. So I don't know if there are any questions about this first part.
Could you go a little bit more in detail about the saving conditions that you mentioned that were necessary for minimizer?
You mean the plus and minus 1?
Yeah. Do you have is there easy counter examples or to understand why this would fail in?
So okay, so the only thing, so let's put it this way. So here, plus and minus 1, knowing that your solution was plus 1 and minus 1, which are like the global minima, it forces something strong because it's telling you that the level sets of U they cannot be too wild. So if you think in a ren minus one, right, and R, so let's look at level sets of U. All I'm telling you about the level sets of U is that the level sets of U are graphs, but they could be kind of complicated graphs. Let's look, it could even be this a priori. So let's take just U equals 0. The level set of U equals 0 could be this even, these, and these a priori. This doesn't contradict, right? So this is so U equals 0 would be something like this. Then this is U less than 0. And the part U positive it's here. So you see, assuming only monotonicity, your level sets could be like graphs that go to infinity. While with Savin, the fact that it assumes that at plus and minus 1 you converge to 1 doesn't allow for this picture. It tells you that your level sets look like a bit nicer in some sense. And this makes a huge difference when you try to kind of make his machinery work. So what he uses is that by that assumption, it starts to look at blowdown, so it starts to rescale back. And essentially he knows under his assumption that the only thing you can get are hyperplanes. While only knowing monotonicity is not easy to do that. So in sense, what's missing is the starting point. What are blowdowns of your function? So when you take the picture from infinity, you push it down. Does it make sense?
Yeah. Thank you very much.
Yeah, so the picture in the left is the enemy. Yeah, you're welcome. I don't know if there are more questions. Okay. So yeah, just to, you see here, there is also issue of multiplicity. When you collapse stuff, you could have multiplicity that it grows, right? Because level sets collapse to each other. So you could get minimal surfaces which have higher multiplicity or so on. So it's not so obvious how to start without that assumption. Okay, so this was the very classical setup. But actually, it's just because it has been forgotten. But in fact, it's not only this the classical setup. So let me focus a moment about W. So the interaction potential. So W, I told you that the most classical example is 1 minus U square over 2, the Allen-Cahn. And here something strange happens because the PDE is Laplacian of U equal W prime of U, which is a nice PDE, beautiful, but you see PDEs are non-local in the sense that if I look at my solution U in a ball of radius R, and let's say that I have some level sets, so I have a picture like this. And now here U is very close to 1, here U is very close to -1, and here U is very close to -1, and here these are the transition region. So U is -1, then it goes up very quickly. Well, quickly. It needs a bit of space. So this is a large ball. So this is R, capital R, and I'm looking at my solutions in a huge ball. And let's assume that U it goes up and down. Okay, so that would be my a possible picture that I'm trying to understand how it should look, whether it can happen. So I am in a large ball and I have a solution which is for quite some time -1, then it goes up, becomes 1, almost 1, then it goes down, and then it becomes -1 again. Okay, so if these were just real minimal surface, so U equals 0 now is this, right? So U equals 0 is like this, let's say, and this. So this is U equals 0 and U equals 0. So if the level sets were true minimal surfaces, the two U equals 0 level sets don't see each other. So these are just two independent minimal surfaces. But in my setup, because I'm solving a PDE, the U is global. So it's not that you can just prescribe U somewhere and forget what happens elsewhere. There will be some tail effect. So if I perturb U here, this part will feel it very mildly, but it will feel it. And there is this critical scale of interaction, and the critical scale is R over log R. So if you have a solution in a ball of radius R, then two level sets interact as long as R over log R, so the distance between the two level sets is above or below R over log R. So if you are able to make the two level sets get farther and farther, so let's say much farther than R over log R, then you're happy. The level sets will interact very little. But if they're a critical scale, R over log R, they kind of interact at some scale. So they kind of interact with some non-trivial force between them. So you cannot just say, oh, the perturbation is negligible. So that's the kind of picture we face. And this is just due to the fact that the PDE just sees everything. Okay. But this interaction is kind of comes from the model, right? It has nothing to do with minimal surfaces. So motivated by this, actually, there have been many papers in the 90s about Cahn and variance. And there have been in particular some papers by Caffarelli Cordoba in the early 90s. And then also David Jerrison in the early 2000s. And what they both, the three of them, pointed out is that perhaps rather than working with this smooth potential W, we could work with something more extreme. A potential W which behaves like this. So this is essentially you take 1 minus U square. Instead of square, you put a parameter alpha, and then you let alpha tends to 0, and this converge to 1, and then it has a jump. So the W prime becomes a delta. It's a delta now. It's a Dirac delta. So it's a delta at 1 minus a delta minus 1. So it becomes a kind of a singular PDE. But this is nice because actually it looks singular, but it's not that bad. What happens in this new picture now, if you have Laplacian of U equal W prime of U, well, W prime is 0 everywhere here. So what happens is that if you think of the picture above, the picture will be like Laplacian of U equals 0, and actually U will be just identically minus 1. It has no problem. Constants are harmonic. Then there will be a transition later here. And then here, this is the level between, so minus 1 less than U less than 1. Then there could be another region where U is identically 1. Then another transition layer. And then U identically minus 1. And what's happening here in these transition layers is that the Laplacian of U is 0, because W prime is 0. But then on the boundary, so let me zoom here at the transition, you have a condition at the interface, and the condition you get is that the gradient of U is 1. And the same here. And everywhere else. So instead of having a global PDE, now you have patches of 1s and minus 1s, plus transition layers. And inside the transition layer, U is harmonic. And on the surfaces, the gradient of U has constant modulus 1. So the beauty of this variant is that now the PDE becomes much more local in some sense, because once you can have these patches of 1 and minus 1 that kind of separate the level sets. So that's very nice, because in some sense you don't have this artificial interaction between level sets that comes just because of the other model. Of course, there is still a challenge, because you can still have pictures like this a priori. I mean, it could be the level sets could do like this and like this, and then get away. So it's true. I mean, it's true that you don't have faraway interaction. So this is like U equal 1, U equal minus 1, U equal minus 1, maybe. And you could have U equal 1 again, something like that, a patch. And it's true that so this part of the boundary will not see this part of the boundary, but in some sense they see each other because they're glued, they are connected by necks, which is like a minimal surface, right? So you have minimal surface connected through necks, and then in some sense it's true that locally they don't see each other, but they see themselves globally. So it is a picture which is much more reminiscent of minimal surfaces, I will say. Still, you have the same challenges as for minimal surfaces. Okay, so this is the status. And so just at the local picture, let's try to understand what's happening here. So here, what's happening, I told you, is that here the function is harmonic. and the gradient of u is identically 1 on the surface. So here, on each surface, here and here, gradient of u is 1. And in the middle is harmonic. So this is what we call a free boundary problem, which is called Bernoulli. Which corresponds to look at solutions of the form, let's say, u equals u equal -1, let's say, or u equal 1, but it's u equals 1. Laplacian u equals 0. So I'm just, this picture I'm drawing now is a zoom of this. So I'm trying, take this point, zoom it, move it here. Laplacian u is 0, and then here, Morgan u equal 1. So this is what we call a free boundary problem. And we will need to understand, first of all, if we want to run this machine on a minimal surface, we want to understand a bit the local geometry. And I will not enter now into Bernoulli, it would be too much. But essentially, let me just mention one theorem that we have to prove here. The theorem is, so U global solution of Bernoulli. Oh, now let me state it. Yeah, let me say it differently. I think it's easier for this talk. So U a solution of V1 in Bernoulli. So U from V1 into R, solution of Bernoulli. B1 contained in R3. For our purpose, is a three-dimensional problem we want to study. Then, and U is stable. So we have the stability. So U stable. You need to write a stability condition as for the Allen-Cahn. Then the level sets, this level set is level set. So U, the boundary of U, okay, U greater than -1, the picture, is universally smooth. What do I mean? I mean that, let's say, the second fundamental form is universally bounded. So the second fundamental form of the free boundary, an infinity of B1 half, is bounded by constant. So essentially, if you have a solution, so this is like a local picture that tells you that for Bernoulli in dimension 3, if you're stable, you cannot create next. So this is just to understand. So here I was just focusing around one point, and I'm saying once you have like universal curvature estimates. Essentially, what this is preventing you is to have in B1 a solution of Bernoulli that does this. So this would be here. The enemy would have been this U equal -1 here, and then here Laplacian of U is harmonic, and gradient of U equal 0. Gradient of U equal 1 here. So a solution like this of Bernoulli doesn't exist in dimension 3 if it's stable. If it's not stable, you can build them. There exists no stable solution, but the stability prevents this, which is similar to minimal surfaces. You cannot have necks and small catenoids if you're stable, because they carry negative Morse index. So we need this to run the next and the last bit, which is the stable Giorgi conjecture. So the theorem we proved with the Fernandez, RT Cahn, Cahn, Fernandez Real, myself and Serra, 25, says the following: in a tree, stable De Giorgi holds in this setup. So the Slasia stable De Giorgi would have been for the Allen-Cahn. Here we work with this W, which is singular, but we have stable De Giorgi, which means that in R4 classical that Giorgi holds. The classic is the one for monotone solutions, the monotone last value. And let me just try to tell you what is the key. How do you approach this? Essentially, here we wanted to go from the classical proof for minimal surface to the solution. So we wanted to mimic what people do in minimal surfaces and export it to this setup. So the core of the argument is this theorem. So this, of all the paper, let's say 75% of the paper is this theorem, these a priori curvature estimates. And then the last 25% is the proof of the Giorgi conjecture. And okay, I will not have the time to go into details for our problem, but let me just tell you in a nutshell what is the idea, because it's a beautiful, simple idea that maybe some of the experts in minimal surface know very well. But if you're not familiar, it's worth knowing, which is how do you prove that stable minimal surfaces in R3 are flat? This is a Pogorelov proof, and the Pogorelov proof goes as follows. Take a minimal surface, sigma, fix a point, x0, and look at the ball of radius r around x0. And I want to understand how much is there of the ball. So the first thing you do is that you do d over dr of the area of the ball inside sigma. So I'm looking at the ball inside sigma. And when you differentiate, you will get the length. So yeah, these are two-dimensional surfaces here, sigma studio. So length of the boundary of BR. And now differentiate one more time. And you will get the integral of the boundary of BR of the geodesic curvature of the boundary. But here you can apply now Gauss-Bonnet because you are on a surface, and you will get minus the integral of the Gaussian curvature over the ball plus the Euler characteristic of the ball. Okay, now the Euler characteristic, this will give you a 2 pi. But in fact, the characteristic is always at most 2 pi. So actually, you only need an inequality here. You don't even need the equality case. And now here you have this. So now you can double integral this. So this is the second derivative. So what we prove is that the volume of the ball, and then you have the term from the Euler characteristic. So minus the integral from 0 to r integral from 0 to s. So ds d sigma of the integral over b sigma of so I'm integrating both sides. So I should do this. So here I integrate, let's see how I want to do it. Minus, yeah, here I just put the Euler characteristic, which is just, the Euler characteristic is 2 pi. Is equal or less or equal, but I only care, but in this case it's an equality. Integral from 0 to r, integral from 0 to s of the integral over b sigma of minus kappa. Okay, so this is just pi r square. And now for a minimal surface, in a minimal surface, you have two curvatures, kappa 1 and kappa 2, 0, 0, but kappa 1 plus kappa 2 is 0. And kappa 1 times kappa 2 is kappa sigma. So actually kappa sigma is just up to a factor is the same as 1/2 of the second fundamental form square. So this is 1/2 kappa 1 square plus kappa 2 square because of this. And now you integrate twice. So you compute this, you use Fubini. And this is the same as 1/4 integral over BR of a square. This is just a simple Fubini. R minus S square ds. Well, here I should put it, yeah, over the ball. So this is ds will be the distance of the geodesic ball. Yeah, maybe I should have used them also. Yeah, better to use the distance here. Sorry. Let me use rho and d rho. So rho is like a polar coordinate I'm using. Rho X, yeah. So I'm just doing a Fubini. Now let's not enter into too much. But the key point is this, that this is my function phi of X in the stability inequality. You remember, my surface is stable. And then for stable surfaces, I have that the integral of A square phi is bounded by the integral of grad phi square. And here I have it. I have a test function that I can just plug it inside, use stability, and then here I get 1/4 integral of the gradient of this r minus rho of x square. So rho of x is really the distance. This is just, yeah, I should have written with rho of x. Rho of x is the distance from the x0. The x, this is just distance from x to x0. And the gradient of the distance is just 1. So this is br, and this is just identically 1. So you get 1/4 volume of br. And okay, and that's it. So you got volume of br minus pi r square less or equal than 1/4 br. You put it together. 3/4 br is bounded by pi r square. So here, this is an inequality that tells you that on a minimal surface, the area of a ball grows almost like r square, which is what you see on a REN, just the volume up to a constant. But once you're there, you are done. Once you're there, you are done. And the reason is just that now you can go back to the stability inequality, and now you apply the stability inequality with a cutoff function, a log cutoff function. So you will just take now on your surface, you take a function which is phi, which is like 1 in a large ball, and then it goes 0 like a log cutoff. So this is your new function phi. And you test it inside, and you will get something like the integral over br over I square is bounded by like 1/log r for r large. And then you let this cancel 0 as r goes to infinity, which tells you that the integral over the surface of a square is identically 0, which means sigma is a plane. So that's the rough idea. So the key difficulty in all these theorems is to prove area growth, to prove that the balls grow exactly as in the Euclidean space. And for us, you see, we are in R3, but the level sets are two-dimensional. So we have a function now in R3, U, which solves our kind of free boundary Allen-Cahn problem, is stable in the Allen-Cahn sense. And ideally, we would like to say, okay, but if perhaps there is hope. So the idea for us is take U from R3 to -1, 1, stable solution. Look at U equals 0. Prove U equals 0 is almost stable. Is essentially stable, almost stable minimal surface outside of the next. Near the next, there is well, I will come in a second, outside of next, and try to run the argument. So here it's an interesting situation because in some sense we don't have, so the difficulty is what? You have an information on U and you want to transfer the information from U to its level sets. And this is in general not trivial because it's like two different levels of solution, right? I mean, you have a variable which is the variable orthogonal to the level sets. So if I have like my transition layer, this is U equal -1, U equal 1, U equal -1, and then you have the level set, U equal 0. So you have an information which is a PD information in the middle, and you would like to restrict the information on the level set. So you need kind of factor out one variable, which in general not so easy. The reason why we can do that is because of this Bernoulli theorem I told you, that it says, oh, but for Bernoulli, stable solutions don't have microstructures. So they have a nice curvature estimates. So this information is what allows us to kind of transport information from the solution to the level sets at most points, but not everywhere. Because if somewhere my solution starts to has some next geometry at some universal scale like this, here there is no way I can do anything. I'm totally unable to relate U to its level sets. And so it means that we don't not only have to run an argument test for minimal surfaces, but we can only run it outside of a bunch of balls. So the global picture we will have will be like a surface that looks like this. So it's like in the classical situation, people don't care. They just run the argument everywhere. In our case, like we have a surface that looks nice, but then somewhere it could have some necks picture. And it could have more necks built. I don't know. Well, it's a 3D picture, so it's not so easy to draw. Maybe there are necks coming out here and there. And then it bifurcates again. And there is another neck, and so on. And every time there is a neck, we cannot run the other argument. So we kind of need to run the argument globally, but to use special cutoffs to control the neck, and then show that in the final estimates, the sum of all the contribution from the necks will be reabsorbed by the main terms that we can bound. So it's like a new proof also for minimal surfaces, assuming that you have a nice geometry outside of a certain number of necks, and you can kind of know how many necks can appear. You have a kind of a density upper bound on how they can appear. So that's the kind of setup. So technically, it gets very technical, but on the main idea is the one I described. Plus, there is all this preparation work on the next. But then, and then the crucial part is the fact that you can relate the level sets. But okay, I think I took all the time I had, so I don't want to take more of your time, and I will stop here. Thank you.
Okay, many thanks, Alessio, for the beautiful and very clear talk. So, are there any questions?
So first, thank you for the nice talk. And my question is, when you have that energy profile W that you took it, I think it was 1 minus U squared over 2. No, you said that solutions behaving in regions, okay, in which they are approximately -1, then approximately 1, and in the transition region, you can consider the level sets equal 0, and there is that non-locality that depends on the distance over the logarithm of the distance, no?
Yes.
My question is about afterwards, when you talk about the result by Caffarelli and Cordova, that exponent 2 is switched to an exponent alpha that you pass to the limit to 0. And then those regions in which you were approximately 1 and -1 now are exactly 1 and -1.
Yeah.
So my question would be, is there still that non-locality that depends on the distance over the logarithm of the distance? Because I don't see it.
No, exactly. So it actually disappears, right? So that's the key point. So now, so actually that's even better. So if you take the 1 minus U square to the alpha, so the classical PDE is 2. The discrete exponent is 2, and that's where you see this interaction. But the moment alpha gets below 2, actually, immediately, then this becomes a free boundary problem. So it gets kind of a singularity at the free boundary, which essentially allows you to kind of make the problem local. So the price to pay is that, so there you see for alpha equal 2, there is no free boundary conditions. I mean, there is no U equal, so you have so if U equal 2, if alpha equal 2, you have the strong maximum principle that tells you that if U is 1 somewhere, then it has to be 1 everywhere. Now, once you get below, the PD becomes so much more singular, and now you're allowed to be 1 somewhere and then just transition to a different So there is no strong maximum principle for the PD anymore. It's singular. The right-hand side is singular enough. And that's the beauty, because now it allows you really to separate. So now when I have level sets nicely separated, so U equal 1 here, and then I have a transition. So these are my true transition layer. In this transition layer, you just have two Laplacian U equals 0, Laplacian U equals 0, plus the free boundary conditions here and here. They don't talk to each other. It's just now I have U equal 1 in the middle, fully 1. So they don't see themselves. The same way as minimal surface don't see themselves. If I have two hyperplanes at distance 1, these are just two minimal surfaces that cannot detect each other. While for the classical Allen-Cahn, if alpha is 2, two hyperplanes are not a solution of Allen-Cahn. I mean, like, you cannot glue one. So there is no analog of two hyperplanes for the classical Allen-Cahn, because they see each other. The level sets see each other. So you cannot like say I go up and then I go down again. Okay, so even in 1D you see this in some sense, because in 1D you could ask, okay, I have the PD U second equal W prime of U. And so now the analog of minimal surface will be points. And there is no, so the Allen-Cahn solution of this is only a function that does this. So it goes from -1 to 1. So there is a transition region, which is your interface. So the minimal surface will be like the main variables. So it's like one upper plane. There is only one. While with the free boundary version, I can always do -1, go up, 1, go down, and so on, and I could keep doing it. So this transition is like one hyperplane in the remaining variable. These are another hyperplane. I can put parallel hyperplanes, and I can do as many as I want, as far as I want, which is a perfect analog of the fact that a stable minimal surface can be made of multiple hyperplanes. Of course, then I have to use the connectedness somewhere to avoid this. So what we prove is that the solution is 1D. And then if you assume, so then the level sets is a union of hyperplanes. And then you need some extra assumption like U equals 0 is connected to rule out this picture. Because otherwise U equals 0 has two connected components, here and here. And I could add more. But this is the same for minimal surfaces. You need to have connectedness to avoid parallel hyperplanes. Does it make sense?
Yeah. Thank you very much.
Anything else?
Sorry, I have a question.
Sure.
Thanks a lot for the talk. It was really very, very interesting. And I was wondering if one tries to apply the same arguments in higher dimension. On one side, Pogorelov, this proof is specific to the 3D case, but the arguments by a Mu bubble to attack the Bernstein theorem and to solve the Bernstein theorem in higher dimensions seem to get bounds like Ln bounds on the second fundamental form. I was wondering whether you think that this is viable, whether the catenoid, the counting and the estimate on the catenoidal neck region are unlikely to extend to higher dimension. Which are the main problems?
Okay, so let me explain now the situation. So there are 2 points. Okay, you could say there is one point. Okay, when we start, it's funny things that when we started on the project, this was actually, it has taken us, I don't know, 6-7 years. So when we started, it was before the results of Chodosh and Lee even existed. So essentially, the minimal surface community was blocked to dimension 3. So we were not hoping ourselves to go beyond that. Then the results came out, and then we asked ourselves, okay, how much of what we did could be extended? There are some hopes, but still requires work. So one thing is that, of course, our proof is very much mimicking Pogorelov argument. But you could say, okay, perhaps we could try to mimic now now there are 3 proofs for dimension 4. So there are 2 proofs by Chodosh-Lee, and then a third proof also by Catino and
Mastroliero and Coroni, yes.
Exactly. So there are 3 proofs. So maybe one of them could be used. So one could try to mimic them in some way. You need to build a green function on level sets. I don't know. But maybe it's possible. So the point where there is another work to be done, and that's the part which I don't say that it's not possible, but it will require extra work, is our 3D result, curvature estimates in 3D. So we did prove that in 3 dimension, if you have a solution in B1 of Bernoulli, which is stable, then the level sets are nice and smooth. So there are no necks on the level sets of Bernoulli. Okay, so this becomes this theorem. So you have to understand the solutions of this. Laplacian equals 0, and then let's say, let me call it V now. Let's say V is non-negative, and then I assume that the gradient of V is 1 on the boundary of V positive. So I just shift by 1 because -1 is bizarre. So I have to understand this. So this is what is called Bernoulli. Now you could ask yourself, so we proved that this result for stable solution and in 3D. Now you see these kind of results, you could ask yourself, okay, let me try to understand about, let me look for V global. Let's say from assuming that V is global. And then ask yourself, what about global solution to Bernoulli? Sorry, global plus minimizers, even minimizer. Okay? And it turns out that V global plus minimizer of Bernoulli implies V is 1D. And this is true in a Rn for n up to 5. So is the analog of the Giorgi Bombieri, the Giorgi Giusti, just we are far by a couple of dimensions. And this is false, for n up to 4, and then it's false for n greater or equal than 7. And then 5 and 6 are open. So at the level of minimal surface, of minimizers, we don't have a good analog of even the Bombieri, the Giorgi Giusti, Simon's result at the level of even minimizers in dimension 5 and 6. So it means that we are a few dimensions off. So there is a hope in dimension 4 still, because dimension 4, this is true. And now there is Chodosh, Lee, and company. But you see, there is the result like this for minimizers. So if you want to prove anything, you still have to remove minimizer with stable.
Yes, I see.
And prove this in dimension 4, which is something which is still open. Okay, so our result in some sense proves this in dimension 3. That's what we did. We classified global stable solution in dimension 3. And then for minimizers is known up to dimension 4. So we need first to improve the understanding of Bernoulli, and then from there we could try to mimic so the Bernoulli part is what tells you how much locally the solution behaves like a minimal surface. And there are parallels just with mismatching in dimension, but all these proofs are very much mimicking the minimal surface classification of minimal cones. But yeah, so that's why we did only at the moment dimension 3. So is it out of reach? No. Is it impossible? No. But it requires for sure more work, because this is still open, the n equal 4 case for stable, just at the Bernoulli level.
Okay. Thanks a lot. Thanks.
You're welcome.
Okay, so anything else? Well then, thanks Alessio again.
Pleasure. Thanks.